Let's do some examples. We'll do 2 of them, and we'll do more examples in class. Well, let's solve following dy dt, sorry, dx equal to x minus 5 over y squared with initial data y0 equal to 1. Okay, so that was the example from the first clip. This is indeed separable. And yeah, so this will be our h of y. All right. So first step was find stationary solutions. But we see that h of y equal to 1 over y squared is never 0 for all y. So we have no constant solutions. Right, so let's start. So step 2 was easy. We just separate, right? So we have dy dx is equal to x minus 5 over y squared. And we separate. So we bring the y squared on the left and the x on the right. And that's all there is to it. And third, we integrate. We integrate the left guy on y and the right-hand side guy on x. And we add our integration constant. Now let's integrate this. So this guy here, we'll do it like this. So this is y cubed over 3, the antiderivative. And this guy is x squared over 2 minus 5x plus our integration constant. What do we do now? Now let's find our c. So what is c? So we put x equal to 0, y cubed 0 over 3, 0 squared over 2 minus 5 times 0 and constant. Y cubed to, and yeah, recall our initial data. So that gives us 1/3 is equal to C. All right, now let's find our solution for this particular data. So what is it? We have cube. So we let's do a step by step. So x squared minus 3 times 5 are 15 plus 3 over 3. And now just take a cubic root. So yeah, right, because 3 2 square minus 15x plus 1, 1 over 3. Okay, so this is our solution. Let me explain the figure from the first clip because it corresponds to this example. So let me rewrite the equation. Plotting solutions for different constants. So I did this with MATLAB. Different C. So again, we had y over 3 and x squared over 2 minus 5x plus c. And all I did was I had different values for c. So right, so let me take you up again. Here. So if you put, so this curve right here corresponds to y over 3, x squared over 2 minus 5x plus 50. Okay, and the guy in the far up is y over 3 and x squared 2 minus 5x minus 50. Okay, so I simply plotted these two curves. Okay. Right. Let's do now. Let's do one more example where the solution is implicit. We'll see what that means. Okay. This is the complicated one we wrote. So an example with an implicit solution. This is the one from the first clip. So dy dx, x squared plus 1, sine of y, plus e to the y. And the initial data is y0 equal to pi. And we'll see why this is a convenient value. All right, so again, x squared plus 1 times cosine y into the y. We see that the h of y is never 0, so no stationary, no constant solutions. Okay. Second step, we separate. So we have cosine of y e to the y dy, and then x squared plus 1 dx. So only y on the left and only x the right. We integrate. So you don't have to do all these steps. You can directly jump to the integration, of course, to save you time. So we have this, and then the integral in x, plus the constant. Okay, so I did that. That was, I mean, you can see it from here. This is the antiderivative of cosine is sine, exponential is itself, x cubed over 3, and then x plus our integration constant. And here we cannot solve for a for y. Here we cannot isolate y because sine of y is non-invertible, right? So this is sine of y, and it fails the inverse test, right? Okay, so this is a solution that's called an implicit solution. A solution that satisfies an equation that cannot be solved. You know, that cannot be, if you like, factored, that cannot be solved for y. Okay. I should finish by putting in the initial data. So for x equal to 0, we get sine of y0 plus e of y0, 0 over 3 plus 0, and then the constant. But that's why it's useful here. Y0 was pi, so we have sine of pi, pi equal to constant, but sine of pi is 0. So we get c to be e to the pi, and the implicit equation is the following. Okay, all right. So we'll do more examples in class. Thank you.